We're heading into the final few pieces of information that we need to know from Unit 5. And so far now we've talked about 4 different ways that you can calculate the enthalpy change for a reaction. We've talked about the enthalpy change is equal to Q over the moles. We've talked about using bond energies, taking the bond energy of the reactants minus the bond energy of the products. We've used enthalpies of formation, and we've also used Hess's law. Okay, now one of our final ways to talk about enthalpy and how it relates to how spontaneous or thermodynamically favorable a reaction is our discussion of entropy. So again, notice the difference. They look very similar to each other. They are 2 very different things. Okay, and so when we think about something having a negative delta H value, we're thinking of it as it's exothermic. Well, if it's exothermic, it releases energy. It's always going to be thermodynamically favorable. Okay, and then we're going to be using that term quite a bit over the next couple days. Thermodynamically, there's a C in there. Favorable. Okay, really just means does the reaction happen without any outside influence. So, and we know that if it is exothermic, that the products do have a lower enthalpy than the reactants do. Okay, and again, we think, well, that's always going to happen, but again, that's not necessarily so. Okay, if a reaction does have a very high activation energy, it might still be exothermic, but it might not occur simply because it might not have enough energy to get started. Once it did get started, then sure, it would keep going, but however, that doesn't always necessarily happen. Okay, for example, the oxidation of ammonia by oxygen to produce nitrogen monoxide and water. The enthalpy change for that reaction is a negative 909 kilojoules per mole. Okay, that's showing that ammonia and oxygen are very unstable. However, this reaction does have a very high activation energy, and as a result, we can say that the reactants are kinetically stable, and that reaction does not occur. Okay, now likewise, backwards, we oftentimes think, well, if something is endothermic, it has a positive delta H. The products, again, do have a higher enthalpy than the reactants do. Okay, we would think, well, those reactions aren't going to be thermodynamically favorable. But again, sometimes they do proceed. For example, dissolving potassium chloride in water has a positive delta H. It's an endothermic process to break that attraction between the potassium and the chlorine. However, the reaction does still happen. So clearly there's more going on than just that, whether it's exothermic or endothermic. Okay? In this reaction up here above, there's also an activation energy that must be obtained before the reaction will proceed. We can say that the delta H value and the activation energy, therefore, are not the only factors that determine whether a chemical reaction will or won't take place all by itself. Okay, and what that leads to is it leads to this idea of what we're going to call entropy. Okay, by carefully examining the process of potassium chloride dissolving, we can see that there's a change from a relatively ordered or an organized state, which is a solid. So the potassium and the chloride ions, remember there's that lattice structure that forms in an ionic compound. And then when it dissolves in the water, it's a relatively less ordered state, okay, or a disorganized state, or a more random state where you've got potassium ions and chloride ions kind of just moving around in the water. Okay, and that is what we call entropy. Okay, entropy, the degree of disorder in a reaction, is called the entropy, and the symbol that we use for that is a capital letter S. Okay, in the reaction above, when you go from KCl solid to K plus Cl minus, which are aqueous. Okay, we can say that the amount of disorder or the amount of randomness has increased. So in the reaction above, there's been an increase in the disorder, which means that there's been an increase in the entropy. Okay, and in such cases, delta S, the change in the entropy is positive. So in this case, going from a solid to 2 aqueous is much more disorganized, and therefore delta S is a positive value. If you're going from, say, aqueous to a solid, that's becoming more ordered, more organized, and therefore delta S would have a negative value associated with it. Okay, now remember that with enthalpies of formation, we said if something's in its elemental form, it has an enthalpy of formation of 0. Okay, with entropy, that's not true. Okay, what affects entropy is motion, is movement, it's vibration. Okay, and only when a pure, perfect crystal at 0 Kelvin, only when you're at that temperature, that's when things have an entropy of 0. Okay, if there's a temperature, if it's above 0, then everything has some type of randomness, disorder, motion, movement about it. Okay, so something's in its elemental form, O2 gas, absolutely has an entropy associated with it. It does not have an enthalpy of formation associated with it, though. Okay, so all things that are greater than 0 do have an entropy associated with them. The state, temperature, and number of particles, though, are important factors in entropy. So, in general, this is something that we're going to be able to figure out. The entropy of gases is much, much greater than the entropy of liquids, which means if you're going from a liquid to a gas, that again is a positive delta S. That's an increase in the disorder. Or you go from a solid to a liquid, or I'm not sure why it's doing that, or from a liquid to a gas, that same thing, that you're going to increase the amount of disorder, and again, that is a positive delta S. Okay, if you go from, let's say you're going from all liquid to all liquid, or all gases to all gases. Okay, let's say you go from 5 gases to 10 gases. Again, that's an increase in the entropy. When you increase the number of particles, you're increasing the amount of disorder. Okay, if you go from a small volume to a large volume, the particles have more room to move around. And so in that case, again, that's a positive delta S. And then again, even if just the temperature goes up from a low temperature to a high temperature, that is an increase in the entropy because you have more energy, etc. Okay, so let's look at these examples here. Okay, so the first one, A, you're going from a solid and a liquid to just a solid. So this side, because it has a liquid on it, and this side only has a solid on it, okay, that is going to be a negative delta S. It's becoming more ordered because you're going from a solid and a liquid, which again, think about motion and movement and all of that, just the solid is going to be much more organized than that. Okay, on letter B, you're going from a solid to a solid and a gas. Again, anytime you produce a gas from a solid or a liquid, that's always going to increase the disorder, which that is absolutely a positive delta S. Okay, letter C, we can see are all gases. So really, it's just a matter of how many. This side, we have 6 gases all total. This side, we have 7 gases all total. More gases means more disorder. That is a positive delta S. Okay, on letter D, let's start think a little bit more here. This side, we have 15 gas particles. This side, we only have 8 plus the liquids. The liquids, again, when you're talking about gases, they're so much more entropic than liquids are that we really don't even need to consider those. So we're going from 15 gases down to 8. That is going to increase the order, which is a negative delta S. Okay, letter E, you're going from 3 gases to 1 gas. Again, that's a negative delta S. And I don't know if there's any of them in here like this or not. Oh yeah, looks like there is. So we'll get to one here in just a second. Okay, letter F, you're going from 1 gas particle to 2 gas particles. Again, more gas particles means more disorder. That is a positive delta S. Okay, on letter G, again, don't worry about the liquids when there's gases involved. You're going from 5 gases to 4 gases, so that is a negative delta S. And then on our last one, letter H, this is what I was talking about. You've got 2 gases on this side, and you've got 2 gases on this side. So in that case, we can predict that there is no noticeable change in the entropy. So again, the change in the entropy is going to be very close to 0. Okay, example 2. Which of the following has a greater entropy? A metal at 273 or the same metal at 400? Again, as the temperature goes up, the amount of movement goes up, the more disorder there is. So the same metal at 400 Kelvin is going to have the greater entropy. Okay, letter B says a flexible soft metal like lead or diamond, a rigid network covalent solid. Again, if it's soft and flexible, that again leads to more motion, leads to more disorder. Therefore, the soft, flexible metal would have the greater entropy. Okay, and then letter C, 2 samples of the same gas at the same temperature, but one with a pressure of 1 atmosphere, one with a pressure of 0.5 atmospheres. Again, if it's the same gas, the same temperature, think about PV equals nRT. If it's the same gas, R is the same, the temperature is the same. If the pressure's higher on one, then the volume is going to be lower in that same gas. So if the pressure's 1, if something's at a pressure of 0.5, then its volume is going to be higher. So when we set up here earlier that entropies of gases with a large volume are more random than entropy of gases with a small volume. So the lower the pressure, the greater the volume, and therefore, again, the greater the entropy. Okay, just like with enthalpies of formation, we can figure out the entropy change for a reaction, again, at the standard state, can be found by subtracting the absolute values of the entropy of the reactants the products minus the absolute entropies of the reactants. And again, they would have to give that information to you, but you can absolutely, just like enthalpies of formation, calculate the entropy change for a reaction if they give you the entropies of each individual component of that solution. Okay, so for example, calculate the entropy change delta S for the formation of ammonia below, and then they give us the entropies. So we know that the entropy change for the reaction is going to be the entropy of the products. So NH3 is 193, and there's 2 of them. So 2 times 193, and that's all of our products, minus the reactants. So nitrogen is 192 plus hydrogen, which is 131, and there's 3 of them. 3 times 131. So I'm going to take 2 times 193 minus, and then in parentheses, 192 plus 3 times 131. Close my parentheses, and I get a final answer. The delta S for the reaction is negative 199. Okay, does that make sense in terms of disorder? So without even looking at this number here, would you have predicted that this value would be a negative value? Well, you're going from 4 gas particles here, 4 gases, to 2 gas particles here. Absolutely, we would have predicted without even doing a calculation that our number would be a negative value simply because you're reducing the total number of moles of the gas. Okay, now when you measure entropy, you'll notice here that many times they give that value to you in joules. So when they give you that value in joules, just know that many times when you use delta H, and in our next lesson we're going to talk about delta G, typically those are measured in kilojoules per mole. So you're very likely, if you do an equation that involves delta S and delta H or delta G, you're going to have to do some converting there. All right, and that's it for entropy.